Hi, sorry about that technical difficulties. Let's continue where we left off. So now we're going to do another example. And so this example is find the area under the sine curve from x equals 0 to x equals 1. So x equals pi over 2. Okay? And so solution, we'll let capital A be that area under the sine curve from x equals 0 to x equals 1. That's its differential from 0 to pi, 0 to pi over 2. Differential from 0 to pi over 2 of sine x dx. Okay? So remember, the derivative of cosine x is negative sine x. So the derivative of negative cosine x is sine x. Okay, so the derivative of negative cosine x is sine x. And so negative sine x is an antiderivative of cosine x. And so we're going to say this is equal to negative cosine x evaluated from 0 to pi over 2. And that's using the evaluation theorem. So this is from the evaluation theorem. So I'm going to put a star there again. That's due to the evaluation theorem. This equals sine. This is an antiderivative of that function evaluated from the lower limit of the definite integral to the upper limit of the definite integral. And so this is negative cosine of pi over 2 minus negative cosine of 0. Okay, so I'm going to open to the bracket here. This is the function at pi over 2 minus the function at 0. I'm going to erase this. Okay, well, what's cosine of pi over 2? It's 0. And if you look at the cosine graph, this is the graph of cosine from 0 to pi over 2. When x is 0, when x is pi over 2, the value of cosine x is 0. This is equal to negative 0 minus negative, and cosine of 0 is 1. So that's minus 1. So this is negative 0 minus negative 1. That's 0 minus negative 1, that's 0 plus 1, which is 1. So the answer is 1. Okay? Okay, note. So that example is done. Now note, this symbol, so this, that whole equation, so this is, that is called an indefinite integral. And means capital F prime of x is equal to little f of x. Okay, so this means this is an indefinite integral, and it being equal to capital F of x means the capital of x prime is equal to little f of x, that function. Another note. So this is an indefinite integral, and it means this is a function. This whole thing is a function whose derivative is little f, the integrand. Okay, no, another note. Definite integral from a to b of f of x dx is a number. So this whole fancy notation, this entire thing is notation for a number. Okay, and this notation, that is one of a family of antiderivatives. Okay, this is one of a family of antiderivatives, right? This is the notation for a function whose derivative is little f of x. We showed earlier that a function can have infinitely many antiderivatives. So this is the notation for one of a family of usually infinitely many antiderivatives. This is notation for a function. This is notation for a number. Okay, the definite integral is a number. The indefinite integral is a function. Okay, with specific properties. A specific function, a specific number. It's not any number, it's a particular number, right? And this is not any function, it's a function whose derivative is the little f of x. Okay, so definite integral, indefinite integral. This represents a number, that represents a function. Okay. Table of indefinite integrals. So table of indefinite integrals. The integral of c f of x dx is equal to c times integral of f of x dx. Okay, these are indefinite integrals. Integral of k dx is equal to kx plus capital C. The integral of sine x dx is equal to negative cosine x plus c. Remember, whenever you have to find an antiderivative of a function, you can actually add a constant to it, any constant to it, and it's also an antiderivative. And so an antiderivative, the antiderivatives we're looking for in each of these cases are an antiderivative plus an arbitrary constant. These are the plus arbitrary constants here in these two. Okay, the integral of secant squared x dx is equal to tan x plus an arbitrary constant c. The integral of secant x tan x dx is equal to tan x is equal to secant x plus c. Okay, the integral of f of x plus g of x dx is equal to the integral of f of x dx plus the integral of g of x dx. Okay. The integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, where n does not equal negative 1. So that equation holds for any n not equal to negative 1. Integral of cosine x dx is equal to sine x plus c. Integral of cosecant x dx is equal to negative cotangent x plus an arbitrary constant c. Oh, sorry, this is cosecant squared x. Integral of cosecant squared x dx is equal to negative cotangent x plus arbitrary constant c. Integral of cosecant x cotangent x dx is equal to negative cosecant x plus an arbitrary constant c. Okay, so these are these are 10 more equations. These 10 equations are equations relating values of the indefinite integral. Okay, so those 10 equations are a table for this table of indefinite integrals. Okay, so in this example, let's find, actually, wait 1 second, let me give you some more time to write all this down. Okay, so you have these 10 equations. So for instance, let's look at this equation. You think the integral of secant squared x dx equals tan x plus c. That means that for any constant c, tan x plus c is a function whose derivative is secant squared x. So for instance, if c was 0, then the derivative of tan x would be secant squared x. If c was 15, tan x plus 15, if you took the derivative of tan x plus 15, its derivative would be secant squared x. If you took c equals 1,000,000, tan x plus 1,000,000 is a function whose derivative is also secant squared x. And so for any constant c you plug in here, tan x plus that constant, its derivative is secant squared x. Okay, and so the plus c's being added in all these places mean that you're finding a formula to represent the infinitely many functions, all infinitely many functions, whose derivative is the integrand function. Okay, so let's look at another example. Example, find the general indefinite integral. integral of 10 x to the fourth minus 2 secant squared x dx. Okay, and this is equal to 10x to the fifth divided by 5 minus 2 tan x plus c, or 10 over 5 is 2, so this is equal to 2x to the fifth minus 2 tan x plus c. That is the general indefinite integral of this. Okay? So an antiderivative of 10x to the fourth is 2x to the fifth, and an antiderivative of negative 2 secant squared x is negative 2 tan x. That's used from this formula here. The integral of secant squared x is tan x plus c. That's the integral of negative 2 times the integral, an antiderivative of negative 2 secant squared x dx would be negative 2 tan x. Okay? And then a plus c at the end. So that's that example, using these 10 equations. Okay, so let's keep going. We're going to erase this table. Okay, evaluate definite integral from 0 to 3 of x cubed minus 6x dx. Okay, so let's evaluate that. Let's use the evaluation theorem, the properties of the definite integral. So solution, definite integral from 0 to 3 of x cubed minus 6x dx is equal to, well, let's just use the evaluation theorem. So let's find an antiderivative of x cubed minus 6x, that's x to the fourth over 4 minus 3x squared. And so you're going to take that antiderivative and you evaluate it from the lower limit of the definite integral to the upper limit of the definite integral. Then that's equal to this expression plugging in the upper limit, which is 3. So that's 3 to the fourth over 4 minus 3 times 3 squared. That's the value of that expression plugging in the upper limit here, minus this expression plugging in the lower limit. So it's 0 to the fourth over 4 minus 3 times 0 squared. Okay? And so what is that equal to? The value of this expression is 3 to the fourth, which is 81 divided by 4. 81 over 4 minus 3 squared times 3, that's 3 cubed, which is 27. Okay, so you have 81 over 4 minus 27 minus 0 to the fourth over 4 minus 3 times 0 squared, that's all 0. Okay, so it's 81 over 4 minus 27 minus 0. So this is 20.25 minus 27, that's negative 6.75. That's the answer. Okay, 81 over 4 is 20.25. 20.25 minus 27 is negative 6.75. And that's the answer. Okay, let's do another example. Okay, so see how I have this? This is your integrated function. This is an antiderivative of that, and you're evaluating it from the lower limit of the definite integral to the upper limit of the definite integral. And so then what this means is you take this expression, plug in 3, minus this expression, plugging in 0, and then you just do the calculations, and you get this negative 6.75. Example, find the definite integral from 0 to 12 of x minus 12 sine x dx. Okay, so let's find that definite integral solution. Definite from 0 to 12 of x minus 12 sine x dx is equal to, so what's an antiderivative of that function? It's x squared over 2 minus, actually plus 12 cosine x. That's a function whose derivative is x minus 12 sine x. The derivative of x squared over 2 is 2x over 2, which is x. The derivative of 12 cosine x is 12 times the derivative of cosine x, which is 12 times negative sine x. That's negative 12 sine x there. Okay, so this is the antiderivative of that integrated function, and you evaluate from the lower limit of the definite interval to the upper limit of the definite interval. You get that. The meaning of that, this notation, again, is you plug in the upper limit here, this number, into this expression. You get 12 squared. You get 12 squared over 2 plus 12 times cosine of 12 minus, plug 0 in, you get 0 squared over 2 plus 12 cosine of 0. Okay, that's equal to 12 squared is 144. 144 divided by 2 is 72. This is 72 plus 12 cosine of 12 minus 0 squared over 2 is 0. 0 plus 12 times cosine. Cosine of 0 is 1, so that's 0 plus 12 times 1, that's 12. It's minus 12. And so the 72 minus the 12 is 60 plus 12 cosine of 12. Okay, and so the answer, without calculating cosine of 12 and then doing the arithmetic, leaving as cosine 12, getting the exact value here, that's equal to 60 plus 12 cosine of 12. And so it's not necessarily better to plug into your calculator cosine of 12, get the decimal, and then multiply by 12 and add 60 and get that number. It's not necessarily better to do that, because then your decimal, even if you choose 10 decimal places, a lot of decimal places, it would be an approximation to some nearest to some decimal point, right? If you write cosine of 12 here, then you're actually saying the exact value. Cosine of 12. Putting cosine of 12 there is giving you the exact answer. Okay? So in most ways, I would say this is a better answer than plugging in a number for there and then doing the work on a calculator. Okay? I like that. Okay, so the next example. Example. Evaluate definite interval from 1 to 9 of 2t squared plus t squared square root of t minus 1 over t squared dt. Solution. Okay, so we're going to evaluate this definite integral. So first thing, rewrite the integral we're evaluating. Definite from 1 to 9 of 2t squared plus t squared square root of t minus 1 over t squared dt. Now what I'm going to do is I'm going to express the square root of t in exponential form. So the square root of t in exponential form is t to the 1/2. So I'm going to substitute t to the 1/2 there. It's the same thing. This is definite interval from 1 to 9 of 2t squared plus t squared times t to the 1/2 minus 1 over t squared dt. Okay, so I substitute the square root of t there for t to the 1/2. That's equal to the definite interval from 1 to 9, and it's now going to multiply t squared times t to the 1/2. By laws of exponents, when you multiply two expressions like this with the same base, you just add the exponents. So t squared times t to the 1/2 is t to the 2 plus 1/2. That's t to the 5/2. So this times this is t to the 5/2 minus 1. And that's divided by t squared dt. So that's equal to, now I'm going to take each expression being added and subtracted in the numerator and divide each separately by t squared. This is equal to the definite interval from 1 to 9. 2t squared over t squared is 2, plus t to the 5/2 divided by t squared is t to the, and you just subtract the exponent. So for instance, t to the 5/2 divided by t squared is the same as t to the 5/2 minus 2. You subtract the exponents, and that's equal to 5/2 minus 2 is 1/2. That's t to the 1/2. So this is 2 plus, and t to the 5/2 divided by t squared is t to the 1/2. And this is minus 1 over t squared. 1 over t squared is t to the negative 2. This is minus t to the negative 2. And so I'm keeping this in exponential form, dt. So now I've gotten rid of the denominator here. Okay, So this step was getting rid of the denominator of that fraction. Okay, and now let's just integrate. So an antiderivative of 2, so the antiderivative 2t, evaluated from 1 to 9. Actually, let's just write an entire antiderivative here. So 2t, t to the 1/2. Well, when you add, what you do is you add 1 to the exponent. So you get t to the 3/2, because 1/2 plus 1 is 3/2. Then divide by the new exponent, so divide by 3/2. Minus t to the, add 1 to this exponent, negative 2 plus 1 is -1. And then divide by the new exponent, which is -1. So again, if you integrate t to the 1/2, you get t to the 3/2, because you add 1 to this exponent. And then take the new exponent and divide t to 3/2 by the new exponent. Minus, add 1 to the exponent here, and you get t to -1. Now take the new exponent, divide t to -1 by the new exponent, -1. And so now this, you have this is an antiderivative of that, and evaluate it from the lower limit of the definite integral to the upper limit of the definite integral. I'm going to simplify this expression. This is 2t plus, dividing by 3/2, dividing by a fraction is the same as multiplying by its reciprocal. So dividing by 3/2 is the same as multiplying by 2/3. So this is plus 2/3 t to the 3/2. And then minus, well, minus and a -1 denominator changes the sign to plus. This is plus t to the -1. That's evaluated from 1 to 9. Now it's this expression is an antiderivative of that. I'm sorry, no. This is just simplifying that expression. This is an antiderivative of that. Okay. So now this is equal to, you plug in 9 for that expression, so you get 2 plus 2/3 times 9 to the 3/2 plus 9 to -1 minus this expression for t equals 1. So, oh wait, this is 2t plus. Sorry, this is 2t plus. It's a t and it's a plus. 2t plus. This is 2 times here. It's 2 times 9. Here it's 2 times 9 plus 2/3 times 9 to the 3/2 plus 9 to -1 minus 2 times 1 plus 2/3 times 1 to the 3/2 plus 1 to -1. Okay? And so you take 9 to the 3/2, then 9 to the 3/2, take 9 to the 1/2, that's 3, and then take 3 to the 3rd power, that's 27. 27 divided by 3 is 9. 9 times 2 is 18. So 2/3 times 9 to the 3/2 power is 18. Let me run through that again. This expression I'm circling here, right? 9 to the 3/2. Well, first look at the denominator. That represents 1/2. That's the square root. The square root of 9 is 3. Then cube it. That's 27. So you should be able to do this. 27 times 2/3 is 18. So this is 18. 18 plus 18 is 36. 36 plus 1/9. So this is 36 and 1/9 minus 1 to the 3/2 is 1. That's 2/3 times 1. 1 to -1 power is 1. So you should be able to do this. 2 plus 2/3 plus 1. So that's 8/3. It's 11/3. This is 11/3. So that's the same as 3 and 2/3. Okay. So you have 1, 2, 3, and 2/3. Good. So 36 and 1/9 minus 3 and 2/3. And so that's the same as 6/9, 3 and 6/9. So you just subtract that and you get 32 and 5/9. Okay. Wait. Actually, 33. 32 and 4/9. Not 5/9. Okay, 32 and 4/9. As a decimal, 32 and 4/9. As a decimal, that's 32.44 rounded to the nearest hundredth. Okay, so either 32 and 4/9 is the exact mixed fraction, or 32.44 rounded to the nearest hundredth. Okay, 33. Good. Okay, just calculate. Okay. So that is this definite integral is equal to 32.44 around the clear square. Okay, next is the net change theorem. The integral of a rate of change is the net change. That means the definite integral from a to b of capital F prime of x dx is equal to capital F of b minus capital F of a. So this is the integral of a rate of change. The rate of change is f prime of x. Rate of change, f prime of x is the rate of change, okay? So the integral of a rate of change is the net change. Net change meaning the difference of capital F from a to b, or capital F of b minus capital F of a. Okay, so this is the net change. This is the net change. This is the rate of change. So the integral of a rate of change is the net change. That's the net change theorem. And this is it, right? Capital F is a function whose derivative is the integrand. That's shown there by having capital F prime of x there. Okay. Okay, so that's the net change theorem. Okay, so let's try to put this in. Example. Just on the same board. A particle moves along a line so that its velocity at time t is v of t is equal to t squared minus t minus 6 meters per second. Okay? A. Find the displacement of the particle during the time period (1 less or equal to t less or equal to 4). Okay, so we want to find the displacement of the particle during the time period 1 less or equal to t less or equal to 4. Okay, so let's use the net change theorem for this. The integral of a rate of change is the net change. So the rate of change here is the velocity, right? Velocity is a rate of change. It's the rate of change meters per second. Okay, so to find the displacement of the displacement of the particle is like the net change of distance. Displacement is like the net change in location, and so where you end up minus where you started. So let me just write that quickly. So if you have the definite integral from 1 to 4 v of t dt, which is equal to definite integral of that t squared minus t minus 6 dt, that's equal to an antiderivative of that, which is t cubed over 3 minus t squared over 2 minus 6t. That, an antiderivative of that, evaluated from 1 to 4. And so that's equal to, plugging in 4, you get 4 cubed over 3 minus 4 squared over 2 minus 6 times 4 minus plugging in 1, which is 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. That's equal to, you just calculate this, and 4 cubed is 64 divided by 3, minus 16 over 2, which is 8. So 64 over 3 minus 8, that's 40 over 3. 4 over 3 minus 24, negative 32 over 3. So you get negative 32 over 3 minus 1 cubed over 3 is 1/3 minus 1 squared over 2, which is 1/2. So 1/3 minus 1/2 minus 6. So that's 2 6 minus 3 6. That's negative 1/6 minus 6. That's negative 37 sixths. Wait, it's 2 6. That's 2 6 minus 3 6. Sorry, which is negative 1. Negative 1/6. Which is negative 37 sixths. Yeah. So let me just check this. Get Yes, negative 37 sixths. Okay. So negative 32 over 3 is the same as negative 64 over 6. This is the same as negative 64 over 6 plus minus minus plus 37 over 6. That's the same as negative 27 over 6. Okay, and so in simplest form, that's negative 9 over 2, or negative 4.5. Just need to check my calculation here. Yeah, it's fine. Okay, that's good. Okay, so you get negative 4.5. So that is the displacement of the particle in meters. So it's negative 4.5 meters. So the displacement of the particle is negative 4.5 meters, and this is you could say that function is s of t, the displacement function, because it's an antiderivative of the velocity. V of t is the velocity function, and an antiderivative v of t is the displacement function, s of t. And so you could say this is equal to s of 4 minus s of 1. It's the same as that. Okay, let's go to B. Okay, so B Okay, so for B, we want to find the distance traveled during that time period. So I'm going to erase the net change theorem here. Okay, so for part B, I'm going to give myself space to do this. Find the distance traveled. Find the distance traveled during this time period. Okay, so the distance traveled is different than the displacement. Displacement is the place you ended up, the location you ended up minus where you ended up minus where you started, right? Where you ended minus where you are where you started. That's the displacement. The distance traveled is the actual physical length of the distance you traveled from where you started to where you ended. Okay, from when you started to when you ended. So here v of t is this function. So v of t, this is the solution. V of t is t squared minus t minus 6. Okay, s of t, which is the displacement, is t cubed over 3 minus t squared over 2 minus 6t. That's an antiderivative of s. Okay, so v of t is the velocity function. S of t is the position function. And we're going to start with the assumption that s of 0 equals 0. So we're going to say that we start at 0 in the beginning. And so when we have a plus c here, because it's an antiderivative of v of t, if I were to plug in 0, I would get 0 plus c, which I want to be 0. So the c is 0 by this given, by what I'm putting here. I'm saying we're starting at 0. Okay? So it doesn't matter where you start for the answer to the problem, right? We want to find the distance traveled during this time period from the given that you know the velocity of the time, right? So no matter where you start, the distance you travel, it doesn't make a difference, right? If I start at 0 and I had a certain velocity each time period, and if I started at 100 instead and I had the same velocity, the distance I travel is unchanged by where I start. Make sense? So since we're trying to find the distance, where you start doesn't matter. And so I'm going to say we start at 0. So that means the plus c here is 0. So that's why I can say I don't need the plus c there. Okay? So, right, because whenever you find an antiderivative, there's actually plus c because any value of plus c there would be an antiderivative. And so by this choice, I'm correspondingly choosing c there to be 0. Okay, so find the distance traveled during this time period. Okay. Well, let's do this. I'm going to call this notes. This is like side work here. This is v of t, right? Let's, for a moment, without knowing why, let's take v of t equals t squared minus t minus 6 and set it equal to 0. Let's find when your velocity is 0. So let's factor this out. We have t minus 3 times t plus 2. That equals 0. So t minus 3 times t plus 2 is factoring out t squared minus t minus 6. So you get that from pre-calculus. So t minus 3 times t plus 2 is 0. That means either this factor is 0 or that factor is 0. So either t equals 3 or t equals negative 2. Okay? Right, so the time interval again was in part A, but it's the same time interval. The time interval is from 1 to 4. Okay, so t equals negative 2 is a reject answer because it doesn't apply to this problem. It doesn't fall in that range of t values. Only t equals 3 does. So only when t is 3 is the velocity 0. Okay, so what does that mean? Well, let's think of a side example for a second. Let's say you were a car. Right? You were in a car, and it's driving, right? And so you're driving forward along the road at 20 miles per hour, right? And so then let's say you then change direction. And let's say once you get here, let's say you decide I want to go in the opposite direction. And so then you start driving in the opposite direction, but then you stop here, okay? So you move forward a certain distance, and then you decide you want to go back. So then you go in the opposite direction. Well, in order to change direction, in order to start going in the opposite direction, you can't just go from forward direction to backwards direction without stopping, right? So before you can start going backwards, if you start going forwards, before you can go backwards, you have to stop moving. Your velocity has to be 0. Okay? And so we want to find the distance traveled during this time period. It's not enough to take your final endpoint where you end up minus where you started. Because during your journey, you could have changed directions. Right? Saying that the total distance traveled is where you end up minus where you started would be assuming that you're always going in the same direction. But if you move forward and you move back, the distance of where you started minus where you end up, that's the displacement, is not the same as the total distance traveled. You actually traveled all the way forward here and then traveled all this distance this way. The distance traveled would be this length plus that length. But instead, by calculating the final point minus the starting point, you're only getting this amount of space. That's called the displacement. So that's what we solved in A, the displacement. So in order to fix that, we need to determine where in your car ride was the velocity of the car 0. Those are points in time where you've stopped. And then finding the displacement between those points where you stop in adding up those displacements is finding the total distance traveled. So here it says t equals 3. Okay? So that means that, let's look at, so you have the interval from t equals 1 to t equals 4. Okay? And then somewhere along that journey, you're at t equals 3. We keep calling it journey. At t equals 3, the velocity is 0. So here we're going to put the velocity, v of t. Okay? This is t. T, v of t. V of t at t equals 3 is 0. Okay? When t is, let's say, 2, if you were to plug in 2 here, you get 2 squared minus 2 minus 6. V of 2 is 2 squared minus 2 minus 6. That's negative 4. So here you have negative velocity. Let's say you do t equals 3 halves. Well, if you plug in 3 halves here, v of 3 halves is 3 halves squared minus 3 halves minus 6. What is that? That's 9/4. That's 2 1/4 minus 3 halves minus 6. That's still negative. This is negative. So it's still negative. Okay. So what's happening here is that your velocity is you're going in a negative direction, then you stop, and you keep going in a negative direction. Okay? And so you're going, let's say the positive direction is right, then the negative direction is left. So let's say you're going left from t equals 1 to t equals 3, and then you stop, then afterwards you keep going left until t equals 4. So what that means is actually that you're always going in the same direction. And so the displacement is the total distance. Okay, and so the total distance then is the same as what we got earlier. So then it would just be, so now the total distance, the distance would be equal to, so it would be s of 4 minus s of 1. And so then that would be, I erased it, whatever, 64 over 3 minus 6 over 2, which is 8 minus 24. It's negative 32 over 3. 3 minus 72, negative 32 over 3. And then, so it's negative 32 over 3 minus, plugging in 1/3 minus 1/2, 2/6 minus negative 1/6, negative 37/6. That's equal to negative 64 over 6 plus 37 over 6, which is negative 27 over 6, which is the same as negative 9/2. Okay, let's keep going. Okay. Okay, so the next section is 4.4, and it's on the fundamental theorem of calculus. Okay, so 4.4 is on the fundamental theorem of calculus. Okay, and so it'll be two parts, and so we need to first do some preliminary math to understand it. So let g of x equal to the definite integral from a to x of f of t dt. Okay, so what does that mean? Let's say you have a graph. This is the x-axis, this is the y-axis. And so let's say you have y equals f of t. Y equals f, this is the t-axis. Y equals f of t. And let's say you start at t equals a, and then let's go to t equals x. Then the definite integral from a to x of f of t dt is the area of that shaded region. So g of x here is the area of underneath the graph y equals f of t from t equals a to t equals x. Okay, so again, the area of that shaded region is the g of x defined by that definite integral. The definite integral there is representing the area of that shaded region. Okay, so as an example, let's say you have this. So let's say you have 1, 2, 3, 4, and you have 1, 2, 3. And let's say you have 1, 2, 2, 2, 3, 1, 4, 1. So you have that, this, that. Okay, that's at 4 there. Just line that up. There we go. G of 1, G of 2, G of 3, G of 4. Okay, so we're going to find each of those G values. Well, G of 1 is the definite integral. Oh, okay, sorry. Also, G of x, I should tell you what G of x is. G of x is definite integral from 0 to x of f of t dt. Okay, that's G of x. So it's the area underneath this curve, y equals f of t. This is the t-axis. This is the y-axis. Okay? And so it's the area underneath this graph from 0 to x. So G of 1 is the area from 0 to 1 under this graph. It's the area of that triangle. That's G of 1, the area from 0 to 1 on that graph. So this is base 1, height 2. So the area of 1/2 times the base 1 times height 2. 1/2 times 2 is 1. G of 1 is 1. That's 1/2 base 1 times height 2. That's equal to 1. G of 1 is 1. G of 2 is the area from 0 to 2. So it's that entire shaded area. So I'm taking the 1 area here. That's area 1. And I'm adding to it the area of this rectangle, which is 1 by 2. So this area is 2. So it's 1 plus 2, which is 3. So G of 2 is 3. G of 3 is equal to the area from 0 to 3. So I'm going to add the area of that. So the area of that is the height, which is 1, times the average of the base, the average of this and that. So this is height 2, that has height 1. So the average of 2 and 1 is 3/2. 3/2 times 1 is 3/2. So I'm going to take this, which is a 1, plus that, the area of this triangle, which is 1, plus the area of that rectangle, which is 2, plus the area of that shape, which is, if you take the area of this guy, right, that this is 1, this is length 2, that has length 1. So the average of these times 1 is the average of that. So that's the average of 1 and 2 is 3/2 times 1. So this is the average. This is the average of 1 and 2. That's 1 plus 2 over 2 times 1. That's 1 plus 2, which is 3. 3 plus 3/2 times 1. 3 plus 3/2. So that's 4.5. That's 4.5. That's G of 3. And G of 4. G of 4 is the area from 0 to 4. So now I'm going to add that. So G of 3 was from 0 to 3, and that was 4.5. Plus, now the area of this, which is a 1 by 1 square, that's 1. So 4.5 plus 1 is 5.5. And so G of 4 is 5.5. Okay? So this is how you calculate G of x for this example. So we're going to use this G of x function to define, to talk about the fundamental theorem of calculus next video. Okay?